Okay, hello and welcome to my channel. Today we're going to talk about the complex K-space. So this is where you would draw the graph and you would, find the pole and see what your wave function is doing. So this is one very useful space that you would like to know and maybe master. So we first remember the scattering wave, which is this. A can also be written as EI delta sine delta EIKX. Okay, so we get our A is equal to EI delta sine delta. And here you can rewritten this as, you put the E into an E minus I delta, so you can put it down to the denominator. So you would get sine delta over E minus I sine delta. Okay, so from this, you have your E here, you can expand it into the form sine and cosine. That would be over cosine delta minus I sine delta. Okay, so this is what you got here. Now we're gonna divide it by cosine to get our tangent delta. So from there, you rewrite this as tangent delta over 1 minus I tangent delta. And remember from last video, tangent delta is equal to beta over alpha minus k. Alright, so we are getting somewhere. K is starting to appear now. Okay, from here, you rewrite your AS as beta over alpha minus k over 1 minus I beta alpha minus k. Right, so from this you can push it down and sort of reposition it to get something A minus I beta minus plus 1, no, minus 1 minus k. Right, so once you have something like this, you can see this part and group it, and this is called a pole in the K-space. So what is a pole exactly? Well, when you draw your K-space, this would be your K-space. A real and an imaginary axis. This is your K-space. So real part would be classified by the alpha. The other one is minus I beta. Okay, so when you have something like this, say that your alpha is here and your beta is here. Right, your minus I beta is here. Draw that, and the point here would be the pole. And this pole here specifically would indicate resonance that happen when the energy is at this level. Okay, so I prepared for you some example you to see the other cases. So we take a look at 4 cases. So we're gonna take a look at 4 cases. So we have K1, K2, K3, and K4. So K1 here is going to be 2i, K2 is minus 3i, K3 is 4 minus i, and K4 is minus 4 minus i. Okay, and the wave we're gonna take a look at here would be a free wave. Okay, x. All right. So first is your k1. So k1 is 2i, meaning that it is on the imaginary axis, purely on the imaginary axis. Okay, so would be somewhere, say here. That would be your 2i, or k1. Okay, so this is, take this the point k1. Right, and this point here on the positive value of the imaginary axis of k, this would indicate bound state. Okay, so that is the general rule. When you have your k to be equal to I beta, that would indicate a bound state. Okay, next is our k2 equal to minus 3i. So that would be somewhere down here. This is your k2. And here on the minus side of the imaginary k-axis, this we can generalize it to be equal to I beta, and this would indicate a virtual state, which is similar to a quasi-bound state. You can technically think of them as the same thing, but maybe you can find some differences. I don't really know. Next is our k3. We have 4 minus I, meaning that it would be around here somewhere, so be on this quadrant. So I can just take this pole here as k3, and I generalize that to be equal to alpha minus I beta. And what would this indicate? Well, as I mentioned before, it is a resonance state. Resonance. And here would be somewhere here. This would be your k4. And here, again, generalize that to be equal to a plus. Wait, no, it's minus a minus alpha minus I beta. And this would also indicate a resonance state. So all in all, you can say from this complex k-space, what you can get is that on here, when your k is lying directly on the positive side of your imaginary k-axis, that would indicate bound states. And when you have a k on this side of the imaginary k-axis, that would indicate virtual states, or some people call them anti-bound. Next is when you have any k that is on this quadrant or this quadrant, that would indicate a resonance state. And next is our sort of trivial part, which is where your k is on these two quadrants here. So when they are in the first or second quadrant, so when k in first or second quadrant, your k would be written as, well, something very similar to this, which is, well, the alpha plus beta, and minus I beta, or maybe you can write it as real part of k minus I imaginary part of k. And when you have this, you're gonna get either a decaying function or a growing function it solely depends on whether your real part and imaginary part has the same or the opposite sign. And your wave function would now look like e minus imaginary k. Maybe I should just write beta minus beta k and ei alpha x. So it's solely dependent on the sign of these two guys that you have here to determine whether it would be a growing or a decaying function. And next case is something that I want to talk about, but you probably won't see this now, is when your k is purely real. So meaning that it is on the real axis. And this would cause an infinite flux in the probability, which is unphysical. So right now we say that if k is on the real axis, that is, it is unphysical and impossible. Right, so that would be the end for today's video. Goodbye.